Lesson 8. Stream gradient and slope gradient. Stream gradient is an expression of how steep a stream or river is as it falls or flows over a certain stretch. Stream gradient is typically labeled with units of feet per 1,000 feet, meaning that the stream drops so many feet per 1,000 feet in length. To determine stream gradient, you'll need to find the elevation at the starting point and at the ending point. You'll need to look closely for the elevation contours and get the best number from them. You may need to estimate the elevation between two contours. Sometimes a flat section of river, called a pool, may have an elevation displayed on the map, and if your beginning or end point is in that section of the river, you may be able to use the quoted pool mean elevation. Once you have the beginning and ending elevations, you can subtract the lower one from the higher one to get the change in elevation, feet or meters. Let's find the stream gradient for the whole run of Falls Creek, high up in the Mount Baker Snoqualmie National Forest on the Damnation Peak Washington Quad map. Let's see if we can find Falls Creek. Well, here it is. Falls Creek starts up here in the mountains and comes on down as a couple of tributaries come into it and empties out into Bacon Creek right here. Let's find the beginning elevation. Well, there it is. Here is the top of Falls Creek where it's known to start. So as you can see, the head of the stream starts between this index contour and this other contour further down. The two. Now, as you come back along here, you can see that the index marker is 3,800 feet in elevation. Okay? And then this next contour down, we have to check the contour interval to see what that is. The contour interval is 40 feet. So we know that other interval has to be, see if I can do the math right, 3660. All right? The head of the creek kind of looks halfway between the two. So why don't we just go with 3780 feet above sea level. As the top. Now let's go down here, follow Falls Creek all the way down till we get to where it runs into Bacon Creek, and we see that there's a couple of contours in the area, but it's kind of flat, and somebody's posted a spot elevation right there, 596. I think that's going to be as close as anything to estimating a contour between here and here. I would be willing to bet this is probably 600, and this is going to be 560. So here's 596. I think we should use 596 feet as our low point. Okay? So, the change in elevation is the top minus the bottom, And yes, I will use a calculator. 3780 minus 596 equals 3,184 feet. Now we'll need the distance along the stream. Note that this is not the distance in a straight line from the start to the end, unless the stream is perfectly straight. Think of this distance as the distance a boat would travel down the river or stream from start to finish. It would follow every turn of the stream, and that's just what you need to do to get the distance. You can use an edge of a piece of paper, or a string, or even wax floss to get this distance. Let me show you how you do it with a piece of paper. Okay, here's our stream. Starts up here, and I'm going to start it right at the edge of the paper, and then at every turn I'm going to sort of pin the paper down with my pen, and I'm going to rotate the paper, and then I'm going to move to the next stretch where I need to rotate and then rotate, and that goes to about here. And I'm going to rotate down like this here. And in this way, I can make the paper follow the contours, or follow the winds, the meanderings of the stream. And by pinning the paper at that pivot point, we guarantee that we get all these turns. Right there. Now this distance that you've got from the start of the paper where you went with the top of the creek all the way to here is your stream length. One way to figure out how long it is you can bring it to the bottom, and you can use the scales. So for example, looking at feet, here we have 10,000 feet, 0 to 10,000, and then we have 0 to 9,000 more, but what we can do is we can slide that over to the 9,000 marker. And we know that this is 9,000 to here, and then we have these small increments. Let me zoom in on this a little bit. So we had 10,000, then we had another 9,000, okay, and then we have this much, just this little bit left over here, and you can see from 0 to 1,000 feet, this is divided into 5 increments, so each of these is 200 feet, okay, so we can add another 200 feet there, and we get 19,200 feet of stream length. Now to get stream gradient, we take the change in elevation, which we figured out was 3,184 feet. We divide that by the stream length, 19,200 feet, and we multiply that by 1,000. Times 1,000, and we get 165.8 feet per 1,000 feet. And that is our answer for stream gradient. Slope gradient is kind of the same as stream gradient, except that the measurement is for another slope or grade and not a stream or river. The pathway for this slope could be a road, a railroad, or just the terrain. It could be a straight line, or it could follow a winding path just as with the stream. Terminology-wise, gradients refer to streams and rivers, grades refer to man-made works, and slopes refer to natural terrain. To find slope gradient, you apply the same steps as above for streams. To determine slope gradient, you'll need to find the elevation at the starting point and at the ending point. You'll need to look closely for the elevation contours to get the best number, and you may need to estimate between two contours. You may also get lucky, and either starting point or ending point may coincide with an elevation marker, called a vertical control station marker or spot elevation. You can double check on those in lesson 5. Those are usually more accurate than estimating from contours. Once you have the beginning and ending elevations, you can subtract the lower one from the higher one to get the change in elevation. Let's consider a slope or grade between where the Boston and Maine Railroad crosses State Route 116 near Amherst College on the Mount Holyoke, Massachusetts quad, and at a point on the railroad approximately 276 feet before the railroad crosses the Connecticut River. Well, here is Amherst College, right there. And here's State Route 116, and here is the railroad coming right up through here. So we need the elevation right here. Now we can see that here's kind of a hill with an elevation of 300, and it goes down a little bit and then back up again over here to over 300. So it's going to be somewhere in between. You can also see on this contour runs around. This is the 200-foot contour right here. So this goes down into a stream. See here, and then there's an intermittent stream that feeds down this way. The contour interval here is 10 feet. I just checked it at the bottom of the map. So for example, here's 200, and we know this is going uphill. So we can say 200, 210, 220, 230, 240, 250, right in through here. And it looks like maybe one more, 260. So we say this elevation is 260 feet above sea level. Now we're going to follow this railroad from this crossing to Boston and Maine. We're going to keep going until we get to 275 feet from where it goes over the river. Okay? Well, 275 feet, if you convert that at 2,000 feet per inch, you can convert it into millimeters. It's about 3.5 millimeters. And surprise, we have a benchmark. A benchmark with an elevation. Okay, so we know that the ending point is at 133 feet. Okay, so we can subtract the two, and we have the change in elevation equals 127 feet. Now we're going to need the distance along that railroad. Note that this may not be, as you can tell from looking at the map, it's not necessarily going to be a straight line. Sometimes we'll get a question for the terrain slope between 2 points, and if they don't give you any other information about the path, then you can assume that's going to be a straight line between the 2 points. But in our case, we're following a railroad. Think of this as the distance that that the train would travel down the path. In other instances, you could be following a path that a person or a car might follow. The train's going to follow every turn of the path, and that's what we need to do to get the distance. Last time we did this with a piece of paper. Now I'm going to show you how to do it with some wax floss, dental floss. And this is going to be, I think, similar to how you would do it with a piece of string also. Here was our starting point. And we can stick this floss. If you press hard, and it's the good waxy kind, it'll stick to the page. Doesn't always, so this will probably work out more like a string. But you basically move the string along the contours, kind of like we did with the piece of paper. And just keep following along the track, going around the turns. And then you can make a mark on the string, or the floss in this case. And now this whole length is going to be the length that we need to measure. Now we're going to do it a little differently than we did last time. Last time we showed you how you can take the edge of the piece of paper or the floss and go down to the scale of the map and read it off of there. This time we're going to do something a little different. We're going to take a ruler and we're going to measure the string like you would measure anything. So we're going to set this at the little mark we made at the starting point. And we're going to see, looks like we have over 30 centimeters. So we make a mark at 30. And we take the rest of it. We measure the rest. 35.1. So we get 35.1 centimeters. I like centimeters because I just find metric easier to work with. So we're going to take 35.1 centimeters and we're going to convert it into inches. So I happen to know that for every 1 inch, there are 2.54 centimeters. And now we're going to go right along, and we know that for every 1 inch on our map, our quad, there are 2,000 feet. Okay, so centimeters will cross out, inches will cross out, and we're going to be left with feet. And we know that we just take 35.1 times 1 times 2,000, divide by 1, divide by 2.54, divide by 1. We don't have to do the ones, obviously. I just put those in so you could see what I'm doing. So 35.1 divided by 2.54 is roughly 13.8 inches times 2,000 feet equals 27,638 feet. Okay? So now to calculate our slope gradient, we take the change in elevation, which was 127 feet. We divide by the total distance, which is 27,638. And now here's the most important thing to remember. Slope gradient and stream gradient aren't the same because they have different units. For some reason, slope gradient is always is feet per 100 feet of length. Okay? Remember, in stream gradients, this was per 1,000 feet. But now for slope gradients, we must do per 100. So we multiply this ratio by 100 to get that result. So we do the math. 127 divided by 27,638 equals times 100 equals 0.459, well, rounds up to about 0.46 feet per 100 feet is our slope gradient for that railroad from Amherst College down to the river. Hope you enjoyed the lesson. Thank you very much.